Hello, geometry students. In this lesson, we're continuing our look at trigonometry, trig ratios. We're going to be specifically talking about complementary angles. Of course, complementary angles add up to 90 degrees. On a right triangle, you will always have a 90-degree angle, and then the other two angles will always be complementary. The yellow and the orange will always add up to 90. That's useful. So a lot of times we will actually notice the notation on this one. I've actually got an angle that I'm calling theta, and then I've got it the other side. Instead of calling it something different, I'm just going to call it 90 degrees minus theta, letting you know in its very name that they are complementary. Notice acute angles of any right triangle are complementary. By the way, it's complementary because it's a completement. They complete each other. It's not like they're saying you're looking lovely today. So, start off with something fairly basic. This is a calculator exercise, or go to the back of the book. If I want to find the sine of 70, the sine of 70, of course, is opposite over hypotenuse. I don't have that information, so I'm going to have to go straight to the calculator. And it's already been calculated for me. For a 70-degree angle, the opposite over the hypotenuse always reduces down to 9397. Well, now look at the cosine of 20. The cosine of the complement of it. The cosine of the complement of 70, which is of course 20, cosine of 20 is also 9397. That's because it uses the same sides. If you think about it, if you're standing here at 70, this is the opposite and this is the hypotenuse. But if you're standing down here, this side that's the opposite turns into the adjacent. And of course the hypotenuse never changes, so it will always be the same numbers in the ratio. So complementary angles have the same, use the same, let me just go ahead and say sine of 20 is equal to 3420. And the cosine of its complement, not the cosine of the same angle, but the cosine of the complement should be the same thing because it uses the same sides. And they are. So that's important to know because if you don't know one of them, you could find the complement. Continuing with this, the sine of 35 is equal to 5736. Somebody has already done that calculation for me. But if you look at the complement of that, if you go to the other corner and use the cosine, it ends up being the same thing. Likewise, the sine of 35, I've actually got the same problem twice here. I want to do the sine of 55. So I'll have to correct that later. If you do the sine of 55, it's 8192. And the cosine of that complement is going to be the same thing. So the sine and cosine, they're co-functions of each other because at opposite corners of the triangle, they actually use the same information. So look at this one. Find the given trig ratio, then simplify. Well, I'm standing here for theta. If you're standing there at theta, identify the hypotenuse. The hypotenuse is always across from the right angle. Doesn't matter how the triangle is positioned. If you're standing here at theta, this becomes the opposite side, and this is the adjacent side. So if it's asking for the sine of theta, it is opposite over hypotenuse. I'm going to leave that. You can get the decimal if you want, but I'm actually going to leave that. The 90 minus theta has to be this angle up here. This is 90 minus theta. If I'm standing up at this corner and I'm looking for the cosine, this automatically becomes the adjacent side. And this, of course, is the opposite side. The hypotenuse stays the same. So if you want the cosine of this purple angle, it's adjacent, which is 12, over the hypotenuse is 20. It's not a coincidence that they're the same because they use the same information. And if you're interested in the decimal to me is not very useful because I want to see opposite over adjacent, opposite over hypotenuse, adjacent over hypotenuse. So complementary angles use the same numbers. Well, how about going backwards? In this case, I'm going to look at the cosine. If you're standing here, for that angle, this is still the hypotenuse, this is the adjacent, and this is the opposite. If you're looking for the cosine is adjacent over hypotenuse. So adjacent is 16 and hypotenuse is 20. But what happens if you go to the other corner? This is 90 degrees. This is 90 degrees minus theta, which I don't know, maybe it's a 35 degree. 90 degrees minus will make it a 55 degree. Doesn't matter, that's what we're calling it. If you're standing at this corner, this becomes your adjacent side, and that becomes your opposite side. So if I'm asking for the sine of this purple, the opposite is the 16, and the adjacent, the hypotenuse is the 20. So it's not a coincidence that they're the same because they use the same sides. They are cofunctions. They work together. So opposite corners are going to have the same information. How about tangent? Tangent's kind of the odd man out because it's a little bit different. But if I'm standing here, this is my hypotenuse. Tangent does not use hypotenuse at all, so I'm going to mark that out. If you're standing here at this theta, this is the adjacent because it's attached. And this is the opposite. Well, tangent is opposite over adjacent, so it's 12 over 16. What happens when you move to the other corner? This angle, I'm not going to call it theta, I'm going to call it 90 minus theta because, again, if that's 35 degrees, that's 55 degrees. Well, if you're standing at this corner, the hypotenuse stays the same. This becomes the opposite side, and this, because it's attached, is now the adjacent side. They just reverse. So the tangent of the other corner is 16 over 12. It's not a coincidence that it's just reversed, because the tangent's just basically the reciprocal of each other. The tangents of the opposite corners are always going to be reciprocals. This is 0.75. It's not as easy to see if you convert to the decimal. It's easier to see with 16 over 12 versus 12 over 16. So tangent is kind of its own